So, Earth's orbit around the Sun isn't a perfect circle, it's actually an ellipse, which means our planet gets closer to the Sun at some times and farther away at others. At perihelion, Earth is about 5 million kilometers closer to the Sun than at aphelion, but surprisingly this doesn't cause the hottest or coldest seasons. Here's the striking punchline. Earth's seasons are driven more by its tilt than its distance from the Sun. Did you know this fascinating fact before? What is perihelion? Well, Earth's orbit around the Sun is far from a perfect circle. It's an ellipse, which means the distance between Earth and the Sun changes throughout the year. One of the most fascinating points in this journey is called perihelion, the moment when Earth is closest to the Sun. This event usually happens around January 3rd when the distance shrinks to about 147 million kilometers. At perihelion, Earth is roughly 5 million kilometers closer to the Sun than at other times, which might make you think it's hotter then. But here's the twist. Perihelion actually occurs during the Northern Hemisphere's winter. This surprising fact reveals that Earth's seasons aren't driven by how close we are to the Sun, but rather by the tilt of our planet's axis. Another interesting aspect of perihelion is that Earth speeds up in its orbit due to the Sun's stronger gravitational pull, moving faster than at any other point in the year. This change in speed follows Kepler's laws of planetary motion, showing how gravity shapes our planet's path. While the extrasolar energy Earth receives at perihelion, about 7% more than at aphelion, does have some subtle effects on climate, it's not enough to override the seasonal changes caused by axial tilt. Understanding perihelion gives us a clearer picture of Earth's dynamic relationship with the Sun and helps scientists predict climate patterns and refine space navigation. It's a perfect example of how the cosmos operates with complexity and precision, influencing life on our planet in ways we're still uncovering. What is aphelion? Earth's orbit reaches its farthest point from the Sun at a moment called aphelion, occurring around July 4th each year. At this time, Earth drifts out to approximately 152 million kilometers away from the Sun, about 5 million kilometers farther than at perihelion. You might expect this distance to make summer cooler in the Northern Hemisphere, but surprisingly, it's the opposite. Aphelion coincides with the Northern Hemisphere's summer, reinforcing that the seasons are controlled more by Earth's axial tilt than by its distance from the Sun. Even though Earth receives about 7% less solar energy at aphelion compared to perihelion, this difference is subtle and overshadowed by the tilt's effect on sunlight angle and day length. Another intriguing fact is that Earth slows down in its orbit at aphelion, moving more leisurely due to the weaker gravitational pull from the Sun. This orbital speed change is a direct consequence of Kepler's laws, which describe how planets sweep out equal areas in equal times. The slower pace at aphelion slightly affects the length of seasons, making Northern Hemisphere summers a bit longer than winters. Aphelion also plays a role in shaping climate patterns, subtly influencing temperature variations and atmospheric dynamics. Understanding aphelion helps scientists model Earth's climate system more accurately and enhances our grasp of orbital mechanics. In essence, aphelion is a reminder of the elegant dance between Earth and the Sun, where distance, speed, and tilt combine to create the rhythms of life and weather we experience every year. Why does Earth's distance vary? Earth's orbit around the Sun isn't a perfect circle, and that elliptical shape is what causes the distance between Earth and the Sun to vary throughout the year. This variation is what creates the points known as perihelion and aphelion. But why does Earth's orbit take this shape in the first place? The answer lies in the gravitational forces exerted by the Sun and other planets, especially giant ones like Jupiter and Saturn. These forces tug and pull on Earth's path, stretching it into an ellipse rather than a circle. This elliptical orbit means Earth's distance from the Sun changes continuously, influencing not just the amount of solar energy we receive, but also the speed at which Earth travels around the Sun. Over thousands of years, these gravitational interactions cause subtle shifts in the orbit's shape and orientation, a phenomenon called orbital eccentricity. These changes can impact long-term climate patterns on Earth, contributing to cycles like the ice ages. Understanding the elliptical nature of Earth's orbit helps scientists explain why perihelion and aphelion happen when they do, and why the seasons don't line up simply with Earth's distance from the Sun. It's a complex cosmic dance shaped by gravity, momentum, and time, revealing how interconnected our solar system truly is. This knowledge not only deepens our appreciation for Earth's place in space but also improves climate models and space mission planning, showing that even the smallest orbital shifts can have far-reaching effects. Effect on Earth's seasons. Earth's seasons are often misunderstood as being caused by how close or far we are from the Sun, but the real driver is the tilt of Earth's axis. This tilt of about 23.5 degrees means that during different times of the year, either the northern or southern hemisphere leans toward the Sun, receiving more direct sunlight and longer days. Interestingly, Earth reaches perihelion, the closest point to the Sun, during the northern hemisphere's winter, while aphelion, the farthest point, occurs in its summer. This shows that the distance to the Sun plays a surprisingly minor role in seasonal temperature changes. Instead, the axial tilt controls how sunlight is distributed, creating the familiar cycle of spring, summer, fall, and winter. The tilt also affects the intensity of sunlight, making summers warmer and winters colder, regardless of Earth's varying distance from the Sun. However, the slight difference in solar energy received at perihelion and aphelion, about 7% more at perihelion, does have subtle effects on climate, such as influencing the length and severity of seasons in each hemisphere. For example, southern hemisphere summers tend to be a bit warmer and shorter because they coincide with perihelion. This complex interplay between Earth's tilt and its elliptical orbit shapes the unique climate patterns we experience year after year. Understanding this helps us appreciate why seasons don't simply follow Earth's distance from the Sun, but are a beautiful result of celestial mechanics working together. Impact on solar energy received. Ever wondered how much difference the Sun's distance really makes to the energy Earth receives? At perihelion, Earth is about 7% closer to the Sun than at aphelion, meaning it absorbs noticeably more solar energy. This increase might seem small, but it actually translates into a significant boost in the amount of sunlight hitting our planet's surface. This extra energy can influence weather patterns and temperature variations, especially in the southern hemisphere, which experiences summer during perihelion. The increased solar radiation can lead to warmer summers and slightly shorter winters there. Conversely, during aphelion, Earth receives less solar energy, which can contribute to cooler temperatures and longer winters in the northern hemisphere. However, this difference in solar energy is just one piece of the climate puzzle. The tilt of Earth's axis and atmospheric conditions play much larger roles in shaping our seasons and weather. Still, the variation in solar energy between perihelion and aphelion subtly affects global climate systems, influencing phenomena like monsoons, ocean currents, and even the timing of plant growth cycles. Scientists closely study these energy fluctuations to improve climate models and predict long-term changes. So, while Earth's distance from the Sun isn't the main reason for our seasons, it quietly fine-tunes the climate, reminding us that even small cosmic shifts can ripple through life on Earth in fascinating ways. Influence on climate patterns. The subtle dance between Earth's distance from the Sun and its climate patterns is more intricate than most realize. While the difference in solar energy between perihelion and aphelion is about 7%, this variation can subtly influence weather and climate systems across the globe. For instance, the southern hemisphere, which experiences summer during perihelion, tends to have slightly warmer and shorter summers compared to the northern hemisphere. This difference affects atmospheric circulation patterns, ocean currents, and even the timing of seasonal events like monsoons. The extra solar energy during perihelion can intensify weather phenomena, leading to shifts in rainfall and temperature distributions. Conversely, during aphelion, the reduced solar input in the northern hemisphere's summer can contribute to milder conditions. These subtle shifts, when combined with other climate drivers like ocean cycles and atmospheric composition, help create the complex and dynamic climate system we experience. Scientists study these effects closely, using data from satellites and climate models to understand how small changes in Earth's orbit influence long-term climate trends. This knowledge is crucial for predicting future climate scenarios and understanding natural climate variability. So while perihelion and aphelion don't dictate the seasons outright, their influence gently shapes the rhythms of Earth's climate, reminding us that even minor cosmic variations ripple through our planet's environment in fascinating ways. Earth's orbital speed differences. So, Earth's speed as it orbits the Sun isn't constant. It actually changes depending on how close or far it is from the Sun. When Earth reaches perihelion, the closest point to the sun, it zips along faster due to the sun's stronger gravitational pull. This increase in speed is a direct consequence of Kepler's laws of planetary motion, which explain that a planet moves quicker when it's nearer to the sun and slower when it's farther away. Conversely, at Aphelion, Earth moves more slowly because the sun's gravitational grip weakens with distance. Now, this variation in orbital speed affects how long each season lasts. For example, the northern hemisphere's winter is shorter because it coincides with perihelion when Earth is moving faster. Meanwhile, summer in the northern hemisphere lasts longer as it occurs near Aphelion when Earth's pace slows down. This subtle difference in orbital velocity influences the rhythm of our year and the timing of seasonal changes. Understanding these speed shifts helps scientists refine climate models and predict how Earth's orbit interacts with other celestial forces. It's a remarkable reminder that Earth's journey around the sun is a dynamic, ever-changing dance governed by gravity and motion, shaping the very experience of time and seasonality on our planet. Historical changes in orbit. So, Earth's orbit isn't, fixed in stone. It actually changes slowly over thousands of years, mainly because of gravitational tugs from other planets, especially those massive ones like Jupiter and Saturn. These gravitational forces cause Earth's orbit to shift in both shape and orientation, and this whole process is called orbital eccentricity. Over really long timescales, this means the distance between Earth and the Sun at perihelion and aphelion isn't always the same, but instead, it varies in a pretty predictable cycle. These slow changes can have some pretty profound effects on Earth's climate, even contributing to natural cycles like the ice ages. When Earth's orbit becomes more elliptical, the difference between perihelion and aphelion grows, which actually amplifies those seasonal contrasts we feel. On the flip side, when the orbit is more circular, the seasonal differences tend to be a lot milder. This orbital variation, combined with other factors like axial tilt and precession, creates these really complex climate patterns over tens of thousands of years. Scientists study these cycles to help understand past climate changes and to predict future trends too. The shifting orbit also affects the timing of perihelion and aphelion, so these points actually move through the calendar gradually over millennia. This ongoing cosmic dance just highlights how dynamic our solar system is, and how interconnected planetary motions really influence life here on Earth. Understanding these long-term orbital changes honestly deepens our appreciation for the delicate balance that sustains our planet's environment, and it's a reminder that Earth's place in space is always evolving. Perihelion and aphelion in other planets. Not all planets orbit the sun in perfect circles and, well, Earth is no exception. Just like our planet, other planets also have those points in their orbits called perihelion and aphelion, the closest and farthest distances from the sun. But these distances can vary dramatically depending on each planet's unique orbit. For instance, Mercury, which is the closest planet to the sun, has a highly elliptical orbit, so its perihelion and aphelion distances are really different, causing some extreme temperature swings. On the other hand, Venus has a nearly circular orbit, so its distance from the sun barely changes throughout the year. Then, gas giants like Jupiter and Saturn have much larger orbits, so their perihelion and aphelion points are millions of kilometers apart, but the relative difference compared to their average distance is actually smaller. These variations affect each planet's climate, atmospheric conditions, and even the length of their years. By studying perihelion and aphelion across the solar system, scientists can better understand planetary climates, orbital dynamics, and how gravitational forces shape planetary paths. It also gives us insight into how Earth's orbit compares to others, really highlighting the delicate balance that sustains life here. This cosmic perspective is a good reminder that while Earth's orbit might seem unique, it's actually part of a vast interconnected system where every planet's journey around the sun tells its own fascinating story. Why understanding these points matters. Understanding Earth's perihelion and aphelion isn't just about, distances and dates. It's actually a key to unlocking how our planet's climate and environment work. Scientists rely on really precise knowledge of these orbital points to improve climate models, which helps predict weather patterns and long-term climate changes. Satellites and space missions also benefit from this understanding, since accurate calculations of Earth's position relative to the Sun are crucial for navigation and communication systems. The subtle shifts in Earth's orbit influence everything from ocean currents to atmospheric circulation, shaping the conditions that sustain life. Plus, studying perihelion and aphelion deepens our understanding of celestial mechanics, showing just how gravitational forces govern planetary motion with incredible precision. This knowledge doesn't just stay on Earth, it also helps us explore other planets and their environments. By appreciating these cosmic rhythms, we gain insight into the delicate balance that keeps Earth habitable. It's a reminder that our planet's journey around the Sun is not just a simple orbit, but a complex dynamic dance with effects on our daily lives and our future. Engaging with these concepts connects us to the broader universe, inspiring curiosity and respect for the forces that shape our world. Thanks so much for joining us on this cosmic journey through Earth's perihelion and aphelion. If you enjoyed diving into these fascinating space facts, don't forget to hit that subscribe button and ring the bell icon so you never miss an update from Space Facts. We absolutely love hearing from you, so go ahead and drop a comment below with your thoughts or any questions you might have about our planet's orbit or really anything space-related. Your curiosity is what keeps this channel alive and thriving. Until next time, keep looking up and stay curious.